Okay, next thing up are exponents, and as you can see, there's a lot of rules for exponents. But a lot of them, if you just kind of think about them logically, they're not so bad to remember. So let's go ahead and look at some of these. So if you have a to the b times a to the c, then your answer is going to be a to the b plus c. So let's say we have 2 to the third times 2 squared. We're going to have 2 is still a on the base, and then to the 3 plus 2, or 2 to the fifth. Okay, and that's because this is literally 2 times 2 times 2 times 2 times 2. So you're just adding up your exponents. Okay, your next one below that is a to the c times b to the c equals a times b to the c. So if we had 2 to the fifth times 3 to the fifth, then all we have to do is multiply our 2 and our 3. So then we have 6 to the fifth. And again, whenever you get stuck on these, if you just write out all of your numbers, it'll make it a lot easier to see. So our next one is a to the negative b, that's, sorry, not a 6, it's a b, equals 1 over a to the b. So if I had 6 to the negative 3, then that would equal 1 over 6 cubed. And then our next one is a to the 0 equals 1. There's no example for that because no matter what it is, it's 1. So, you know, I could have like 47 to the 0, and that's going to equal 1. No matter what that number is, it's always going to equal 1. Okay, then our next one, we've got a to the b divided by a to the c is equal to a to the b minus c. So we could have 4 to the fifth divided by 4 cubed, and that's going to end up being 4 squared. Okay, then our next one, a times b to the c equals a to the b times c. So I could have, let's see, 2 to the third, and then that squared, and that's just going to be 2 to the sixth power. Our next one, a to the power of b over c is equal to the cth root of a to the b. So if I had, let's say, 6 to the 2 over 3 power, then you take your bottom thing outside, so you take the cube root of 6 squared. Our next one, radical a, this whole radical is over the whole thing. The radical of a over b is equal to radical a over radical b. So if I said something like radical 9 over 4, that would be radical 9 over radical 4, or purposely picked those because it goes down to 3 over 2. And then our last one here is radical a times b equals radical a times radical b. This is the rule that you guys use whenever you're simplifying radicals. So if I said radical 75, for instance, that's not 7 times 5, it's 75, then I would want to find if there's a perfect square that I could take out. And of course there is. So I could say, okay, fine, radical 25 times radical 3, which would simplify down into 5 rad 3. Alright, so there's a lot of exponent rules to remember. A lot of them, if you just kind of write out all the numbers involved, then it's a little bit easier to see them. But let me go ahead and show you guys a problem that uses more than one of the exponent rules at the same time. Okay, so something like this, simplified quantity, 2x to the fifth, y to the third, all of that is squared. Then all you have to do is distribute this 2. So you'd have 2 squared. So you'd have 2 squared, then x to the 5 times 2, so x to the 10, and then y to the 3 times 2, or 6. So then you would just have 4, x to the 10th power, y to the 6th power would be your answer. Okay, next up are logarithms, or logs. So the basic idea of logs is that if you have the log, so log base b, a equals c, that's the same as writing b to the c equals a. So basically, like multiplication is a shortcut for addition, aka you know, 3 times 7 would be 7 plus 7 plus 7. Exponents are a shortcut for multiplication, so instead of saying 2 times 2 times 2, you could just say 2 to the third. And then logs are a shortcut for exponents. So it all kind of goes in, you know, in a nice little chain. So let's go ahead and add some numbers in here, so this might make a little bit more sense. Okay, so for instance, they could give you a problem like this. So you've got log and then x, your base is missing here, 36 equals 2. So all we have to do is plug it back into our equation. So basically you're looking for what can you raise to the second power in order to get 36. So all you'd have to do is get the square of both sides, and you know that x is 6. So what they're looking for is for you to fill in a 6 there. Okay, let's go ahead and look at a problem that's more complicated than this one.
Okay, here's a kind of nasty little problem. So the reason that this is a difficult problem is that it's not using numbers, so you're going to have to deal with this using just the properties of logarithms. So it gives you your first two logs, and it says what is the log base a of xy squared. So the first thing to know is that whenever you've got a log of something squared, you can actually move that squared to the front. So log base a of xy squared is going to equal 2 times the same log xy. And then the other thing to know is that when you have a log of two numbers multiplied together, you can separate them out. So you can separate this out into, keep your 2, actually put a parentheses in there. So then you'd be looking for the log of x, and then you can add same log of y. So once you know that you're looking for that, you can use the information that you had at the top. So log base a of x equals, let's see, 5. So I could say this is equal to 2 times 5 plus, and then look at the top, that was t. So then your answer would be, if you distribute it, 10 plus 2t. Now, the important thing to remember is that when you're looking at the log of something raised to a power, that power can come to the front and turn into a multiple, and then, or multiplier rather. And then when you have a log of two separate things, you can add those. Okay, so that's a really complicated log problem. You're most of the time going to get more problems on the left than the problem on the right, but you could get one of the more difficult problems in a test could be the one on the right. Okay, the next thing we've got is imaginary numbers. So basically an imaginary number is a number that when you square it gives you a negative result. So for instance, I is equal to the radical of negative 1. Okay, so radical negative 1 doesn't exist, so we've given it a name, it's I. And if you square it, you would get negative 1, supposedly. The nice thing to know about I is that it's going to cycle through 4 different values. So if they ask you for I to a very large number, you can figure it out. So you have I is equal to radical negative 1. I squared would be radical negative 1 squared, which would be negative 1. I cubed would be negative 1 times radical negative 1, or just negative I. And then I to the 4th is negative radical negative 1 times radical negative 1, which would end up being just positive 1. So it's going to cycle. It's going to go from I to negative 1 to negative I to 1. It always goes in that cycle. So for instance, I to the 5th is going to be I to the 6th, negative 1, then negative I, then 1, etc. And it'll keep on doing that forever. So if the problem were something like, what is I to the 27th power. Okay, great. We can deal with this. So I to the 27th power, you obviously don't want to do what I did at the left and keep going, but you do want to figure out how many multiples of 4 go into 27. So you would note that 24 is the kind of closest number to 27, that's a multiple of 4. So you basically know that it goes through the cycle 6 times. So it's going through this cycle over here 6 times. So it goes 1, 2, 3, 4, 5, 6, 7, 8, etc., 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 and then it lands at 24 at the bottom. So 24 is 1. So then all we have to do is the difference between 27 and 24 will give us the number of times that we're going to have to move. So that's 3. So all you do is you'd start at number 1. Go ahead and number these over at the left-hand side so you can see them. So you'd start 1 would be I, 2 is negative 1, and 3 is negative I. So your answer is just negative I. So you could always sit there and write out all the pattern over and over and over for I, or you just find how many times it cycles through, and then whatever's left over, that's going to determine which part of I you're going to use.